In this lecture segment, we'll look at decompressing LZW compressed data, undoing the compression that we did in the prior lecture segments. In principle, LZW decompression is just a matter of reversing the compression process, but there are a few complexities to discuss, so we'll look at those and walk through two example decompressions. Now, the first question to ask when decompressing LZW data is whether the decompressor needs the dictionary along with the compressed data. And importantly, the answer is no. And it's important because the extra data to store the dictionary would add so much space that it would defeat the compression. Instead, the decompressor assumes the same initial alphabet as the compressor. This much they have to agree on. And thus it has the same initial dictionary. But from there, the decompressor reconstructs the dictionary as it decompresses, using the same algorithm that the compressor used to create the dictionary in the first place. And since the decompressor knows exactly the algorithm that the compressor used to create the dictionary and exactly the initial alphabet, then the decompressor can produce an exact copy of what the compressor had as a dictionary at each stage of the compression. Let's see how this works by decompressing the result of our second example from the lecture on compression. We'll start with the compressed output from that example, highlighted here, and I'll put no gaps between the codes, since we need to show that the decompressor can differentiate one code from the next solely by the current dictionary content and the LZW algorithm. Now, the dictionary starts in 2-bit mode, having 3 entries, since we know that the initial alphabet was ABC. The dictionary stays in 2-bit mode for the first 2 codes, before it goes to 3-bit mode when we add the 5th code, or after we add the 5th code, we should say. So the first code is clearly 10 for C, and I'll start to break this apart a little and put the corresponding decompressed output below. The decompressed output, as you see then, starts with C, and the decompressor now adds code 11 to the dictionary to mimic what the compressor would have done. And here we see an important issue in decompression. Code 11 will represent C followed by something, where the underscore here is the second symbol in the uncompressed data. You may recall it was a B here that's coming up, but the decompressor doesn't know that symbol yet. So it must at least start decompressing the next code in order to learn it. So while the compressor has the uncompressed data sitting right in front of it, it can readily determine the extension symbol to add to each new code, the decompressor has to wait for the next code before it can know the final symbol of the just added code. It's always a half step behind. And as we trace the decompression, we'll end the most recent new code with an underscore and fill that in once we know the first symbol in the next code. So with that in mind, the next code, still 2 bits long, is a 1 for B. So we know the second uncompressed symbol now, and also then the full meaning of code 11, which then must be CB. But of course we also add code 100, the 4th code, which will stand for B followed by something, with the something remaining a mystery until we decompress the next code. Now there are 5 entries in the dictionary, so we're now in 3-bit mode. So with that in mind, here's question 1. What's the next code? And what's the 3rd symbol in the uncompressed data, and thus the missing underscore for code 100? And then what new code do we add to the dictionary? And I should extend the bits here to be 3 bits. So thinking about that for a bit, and coming back from a pause, next code is 000. We are in 3-bit mode, and that represents A. So code 100 stands for BA. And we do have a new code as well, code 101, which will stand for A something. And again, this something is still a mystery. And so the pattern goes. and summarize the decompression process. Number 1, start with the same initial dictionary as the compressor, and add new codes to it just as the compressor did. Obtain the next code, call it C, from the compressed bits. You can tell how many bits it has based on the current dictionary size. Add to the uncompressed data the symbols that C represents. If you are on the second or later code, then also use C's first symbol to fill in the missing final symbol from the last iteration's new code. And then 4, either way, add another new code to the dictionary, representing C extended by one more unknown symbol, the first symbol of the next code. Leave a placeholder in that new code until you learn that symbol on the next iteration. And of course, 5, increase the bits per code if the dictionary size has crossed a power of 2 boundary. And you repeat steps 2 through 5 over and over again. So, with that summary in mind, here's question 2. Use that process to decode the next 3 codes. Leaving the final one for later, it requires a bit more discussion. Show the new dictionary contents and the uncompressed symbols. Coming back from what might have been a bit of a pause there. So we'll decompress first code 100, and that gets BA. Now we can fill in code 101 to represent a B, because the next thing after the A is clearly now a B in the uncompressed stream. And we'll be adding a code as well, of course. Code 110, which evidently represents BA something. We just don't know BA what yet. But we will as soon as we get the next code, 011, which represents CB. So it was BAC that code 110 represented. And we then move on to code 7 added, representing CB and something. And finally then we decompress code 110. And note we are still in 3-bit mode because we have only 8 codes in the dictionary, and 3 bits are sufficient to represent them. But that is about to change. Code 110 represents BAC. So 111 then clearly represents CBB. And we add the 8th code, 1000, representing BAC something. And we're in 4-bit mode. Now, we get to the most clever part of the decompression algorithm at this point. Our dictionary stands at 9 codes and is in 4-bit mode, and our next and final code is 100, code 8. But code 8, 100, is the one we just added, and its final symbol is unknown. The next code's first symbol was supposed to fill that in, but the next code is code 1000. This seems like a catch-22, but it's not. To know the final symbol of code 1000, we need only to know the first symbol of the next code, even if that next code is 1000 itself. We do know the first symbol of code 1000, it's B. So logically, code 1000's final missing symbol must be B. Whatever this is, it's BAC something or other there, right? And the B then is available to fill in the missing symbol. And the final decompressed result has BACB then. We use the code to fill itself in at the last minute. Now, that little twist tends to bother people. So I'm going to try it one more time, kind of looking at it a different way. That little stunt we just did, filling the code in with its own first letter at the last minute, bothers you. Then instead, view it from the compressor's standpoint. When the compressor created code 1000, it had the uncompressed data in front of it, and it knew that the uncompressed symbol after the BAC was a B. So it immediately made code 100 stand for BACB, and then it discovered on the next step that it could use that new code immediately, which of course could only be so if the code started with a B as well as ending with a B. We're just reconstructing then what the compressor must have done. And anytime a code is immediately used after having been created, it must be that the first letter and last letter of the code are the same. So now that we've done one walkthrough, let's decompress this second example case shown in our diagram here, including deducing all the uncompressed symbols and the full dictionary content. You'll find at least one case like the BACB code that we just discussed. And we'll do this by a series of in-lecture questions. So question 3, for starters, do the first 3 codes in this example. Coming back from a pause there. Well, we're in 2-bit mode to start with, so I guess we decompress 01 to represent B, and of course we'll add code 11 representing B followed by something. Still in 2-bit mode, so we next have code 01, and that again gets me B, so I fill in code 11 to represent BB, and I add code 100 to represent BB followed by something. And now we're in 3-bit mode because I have 5 codes. So the third code is 010, and filling in the extra zeros here for 3-bit mode. That represents C. So code 4 must have been BC. But of course code 5, also added, represents C something. So after these 3 steps, we've decompressed BBC, and our dictionary now has these 6 codes. So question 4, be sure you understand any errors you might have made in the immediately prior question here, in the work we just did, and then do the next 2 codes. Coming back from a pause there, you decompress 011, and that represents BB. We fill in code 101 then to represent CB, and we'll add code 110 representing BB followed by something. And we then decompress the next one, which is immediately code 110. So we do the same trick as before. The just-in-time reasoning that we covered earlier applies here. The final letter of the new code 6 must also be its first letter, since it appears as the immediately following code. It therefore has to represent BBB, fill it in just in time and use it, and of course we still have to add code 7, 111, representing BBB something. So this time we had a case where a new code was immediately used, and thus its first symbol was also its last filled-in symbol. Our decompression stands at BBC and 5 Bs, and there are 8 codes in the dictionary. Question 5, of course, be sure you've cleared up any misunderstandings from the first 2 steps, and now finish up the entire decompression. Coming back from a pause there, we decompress 101, and that results in CB, and fill in the last character 111 to be BBBC, and of course add code 1000 representing CB and something, and now we're in 4-bit mode. So we will have 2 more codes to do, and the next one is immediately code 8 again, 1000. So again, it's one of those just-in-time things, in case we hadn't had enough of them already. And the last letter of code 8 will have to be the same as its first letter, thus C. Code 8 stands for CBC. And of course we'll add code 9, CBC unknown. And then we decompress the final code 101, which is relatively simple. That's just CB. Code 9 is thus CBCC, although at this point now there's really no need to add or even fill in more codes because we're done with the entire compression. So the final decompression, BBC, 5 Bs, CB, CB, C, CB.